Okay, welcome back. We will continue with chapter 8. And chapter 8 is going to deal with the attitude determination. Yes, we have done a lot on attitude control, but it's good to actually look at the attitude determination itself. Obviously, I'm going to cover basically a very basic and within the chapter. Of course, we are not going to go into some routines, etc. But it's good to know where actually measurements are coming from, attitude measurements where it's coming from, and how could actually we do the updates in order for us to control this particular any particular spacecraft or matter. Okay, go on. If you look at attitude, there is a what kind of actually attitude we can find. You can do two-axis attitude determination. Of course, the best would be actually axis attitude determination. Now, for example, two-axis attitude determination. It means that it doesn't mean that you have two sensors. You can just have only a sensor. It means that there is a particular axis that actually you are using as a reference. For example, now we have been exposed to, let's say, our three axes in local, vertical, local, horizontal. We have the roll axis. Let's say the roll axis, and we have the pitch axis, and we have the yaw axis. So assume that I have a sensor, let's say a sensor, for example, a sun sensor, and I embark along the z-axis, and z-axis is facing planet Earth, yaw. Now, if I embark that the particular, let's say, sun sensor at negative z, that means that it is actually looking at sun already. So when the z-axis, if you look at the z-axis, and there is a line of sight that you want to look at. You want to look at the line of sight of the sun. Now, when your line of sight is being sort of tilted, that means there are another two axes are actually affected. This is how it is. Assume this particular, let's say this is your, okay, and assume that this has been tilted. Practically, this tilting are going to affect another two axes because they are orthogonal. So technically speaking, if I can sense this axis, one axis, I should be able to tell that this axis has been tilted because of there is some rotational motion either in the other two axes, both or either one of those other axes. So remember this, when you have, let's say, a rotational motion in this particular axis, let's say, so when you rotate this, the two axes are going to actually rotate, right? That means you are inducing a particular angle. So what I'm saying is that now assume that I have this particular axis, I have a tilted angle, which means that I have a tilted angle. What made this axis tilted is it caused by another two axes, or both, or even one of those axes. So which means that when my axis, let's say my pointing to the sun, assume it is actually tilted, I know for the fact the cause is not me myself, but another two axes have caused me. So what I know that now, if I can sense it, I can know that they have rotated that amount which induced me for that tilt. Whereas my axis, or your axis that I have, might not be even having any rotation. So I'm tilted because of another two other orthogonal axes. So the two axis attitude determination is very, very basic, or rather minimum way of doing attitude determination. But don't forget, as far as we are concerned, we say that, well, yes, we have a sun, let's say a sun sensor, we can actually sense, but don't forget, unfortunately the rotation of or rather the rotation of z-axis, you can't actually do much. So what exactly that will happen? You may not actually have a very good sensing. You will never achieve a three-axis sensing. So for a three-axis sensing to be achieved, determination of a orientation of a complete triad. That means what? All those three axes, I know how much you have moved or rotated. So that is what, if I can sense all these three, technically speaking, I can have a very, very good knowledge of what is the rotation, and if I have a very, very good knowledge of the actual rotation, I should be able to actually correct them using my attitude actuators that you've been exposed to. So now, simply by just having a particular, for example, for 3-axis attitude determination, what I can have, maybe I can have a particular, let's say a sun sensor, for example. Then I can have also a gyro added to maybe the yaw axis. So when I have a sun sensor along the Z axis, I should be able to take care of the roll and the pitch motion, or sense the motion. I assume that both of them are basically coupled in any case, let's say. Yeah, so I can actually have that motion detected via my sun sensor, and for my Z, which is the yaw, their rotation or that axis rotation, I can simply have a gyro basically to give me that motion. So if I have a gyro which actually is going to give me the rotational motion of the Z axis, technically speaking, with only 2 sensors, I should be able to have all those 3-axis attitude determination done. So that's how actually this whole thing works. Now, importantly, the 2 is basically determination. As you can see very clearly, 2-axis attitude determination, 3-axis attitude determination. The last one is basically estimation. Estimation is you will have a sensor, then after that you should be running an algorithm. Technically, why? Technically to estimate what is the possible attitude, true attitude. So you need to do the estimate. While determination is practically going to read the output of a sensor, and then you know what is your attitude. So whereas estimation, the actual attitude will come after you run your calculation. So there is an algorithm that we need to write, codes that we need to write to deduce and to estimate the exact estimation. Now, if you have, why we should do that? Estimation, why we should do that? Because sometimes we use a very low cost sensors, attitude sensors. Therefore, we compensate that sensors incapability through some algorithm in on board the satellite to estimate a possible true attitude. Now, if you have so much of money, let's say you have good, let's say mission to run, you may opt for gyro. So when you already have a gyro, you can do a attitude determination easily. Make all 3 axes you can have, and you can do attitude determination easily. Technically, you can bypass the estimation process as well. Okay, one. Now, instantaneous attitude, it tells you exact time a set of measurement should be made available by the spacecraft. A good example is that, let's say I have 3 gyros in all those 3 axes. Technically, instantly I should be able to tell you the exact attitude. Now, attitude state estimation, what exactly that you are doing here is that we have plant. What satellite plant we have already established. That means if you look at satellite plant, we have established very well the dynamics. We have also established very well the top compartment. That means the one actually disturbing your attitude. We put them all together as a dynamics model of a spacecraft. We should be actually running. We should be running those estimation, those approximation in a loop to technically to estimate the to do the attitude estimation. So if you can see, technically this is the accuracy might not be very good in that sense. Yeah, might not be good in very sense. Reason being, a lot of estimation process are there. Okay, and typically you can see most of the algorithms you will use filters like Kalman or even uncentered Kalman filter, basically to get your actual estimation. So there are processes to run. But for bachelor level, I think you need to just know the difference, basically how basically you can get a 2-axis attitude determination and how to do a 3-axis attitude determination with the combination of sensors. Go on. Now, if you look at the satellite flies, and we need to maybe use some landmark or some objects in space which can help us to do the actual estimation or determination. Now, the sun can help us. Why? Because we have sun sensors. So, and I think in satellite technology, you've been exposed to all sorts of sensors on board a particular spacecraft, especially satellite. So sun sensors actually could play a good role here, but unfortunately it doesn't work during the eclipse phase. Planet Earth itself, because we have horizon sensors. Horizon sensors can always help us in order for us to actually estimate our altitude. We have stars, like seafarers, they use all the stars basically, formation of stars to navigate when they are sailing. So we can use that as well when we are actually flying. Then we have also, don't forget, we have the geomagnetic field. The geomagnetic field, we have been using, geomagnetic field have disturbed us, and it creates an external torque which disturbs the satellite. At the same time, we have used also, for example, in a control actuator, passive, active actuators, we have used that through magnetotorques, basically, having the magnetotorques and magnetic field as the source of the torque. Basically, we can also induce torque. So, magnetic field not only disturbs us, it also helps us in order for us to induce torque. But on the other hand, it also helps us to navigate. When, as you can see, certain altitude, when you go higher and higher and higher, when you go very far from planet Earth, the magnetic field gets actually very weak. So having that altitude and then having the actual model, we should be able to, as you can see, we should be able to actually estimate the altitude information that we need. So these are the typical sources that normally we use. We don't put anything which is related to gyro here, because gyro works on an altitude rate, so it doesn't actually depend on external source as a need for information. That means it doesn't use the sun, it doesn't use a star, or even a geomagnetic field or planet Earth. Gyro, you don't need any external, I would say, indicators. It actually detects angular rate, and then from there you do an integration basically to find the altitude. You want. Now, please remember the previous chapter on kinematics, because it's going to be very, very handy. And in fact, it is a slightly a small revision that I'm doing here, because the same thing we have also discussed in our quaternion exercises, our DCM, direct cosine metric exercises, our quaternion exercises. We have discussed this, and you have done that in the class. Now, more importantly, what exactly this altitude determination is all about. Now, we have a reference. Let's say we should have reference when you are flying in space. You should have reference, and more often than not, we always have a lot of actually missions are Earth-oriented mission. So I can say that, okay, we have a reference, and this reference is basically, let's say, Earth-centered reference. So you can imagine planet Earth, Earth-centered system, Earth-centered coordinate system, okay, IJK system. Then you have an orbit. You have an orbit system, and orbit system, what we have in actually spacecraft dynamics control, we have also defined as a very particular coordinate that we have used: local vertical, local horizontal system. Let's roll your pitch. Then we have the satellite itself, the body. So remember, in kinematics, there's always three systems that we talk about. Now, you must understand that we have also discussed this. When you have we want to do altitude determination, that means what? You are going to install, let's say, a gyro, even any other active sensors in the body. And this body is going to measure. So we measure that with respect to initial reference. So therefore, that will be measured. Now, the most important thing is that once the measurement is given, we want to know how you are flying with respect to local vertical, local horizontal. If this is perfect, there won't be any difference between A and B. A and B frame would be parallel. That means what? It will be there won't be any difference of angle. So the idea is that always we want to find the actual deviation of the quaternion between these two frames. Which frame is that? Local vertical, local horizontal frame. It's an orbit frame with respect to the body frame. How the body have moved with respect to the actual local vertical, local horizontal. And how this body has moved, and we should be able to tell by having a sensor on board. The satellite, gyroscope for the matter, with respect to a fixed coordinate system, which is the planet Earth here. So IJK will measure. What we have to do is that we have to now compare the deviation. Now remember, in the kinematics, I have also introduced to you rotation matrix. How can we, from one coordinate system, how can we rotate with respect to another coordinate system? So the exercise that we have done also, you want to find how is body with respect to local vertical, local horizontal. Body with respect to initial is available. So you want to find the difference. So as you can see here, let's say I have two vectors, two measurements, let's say, and in the frame A and B, I told you A is an orbit frame, let's say, example. B is a body frame. 2 is available, and 2 is available at the initial, okay, initial. So what is you need to know is that this is the exact thing always we want to find. The actual deviation between these two frames is what we want to find, and you have done this exercise in kinematics. So the same thing, in that notes also you can see there are 3 systems. So actually, attitude determination is nothing but to find the body, how body deviated with respect to local vertical, local horizontal. That's all it is, with the attitude information. So what is given, all these are actually can be found, or whatever, say, measure, this is can be computed. How this can be computed? This is actually transformation. You can do a rotation. You have a rotation matrix, you should be able to rotate from one axis to another axis. It's easy. Okay? If you have if you use quaternion, then you should know that the actual rotation matrix would be 4x4. Okay? 4x4. Quaternion 4x1 size. So you should be able to rotate from here to here, from here to here. And this quaternion operators, I have also given in the chapter of kinematics, how quaternion can be actually used as a tool, basically, to move from one particular coordinate system to another coordinate system. That means one frame to another frame. Okay, go on. Now, vector measurement. So vector measurement, the first one basically, just as an example, first method will be algebraic method. Now, more often than not, you see, we may not actually be exposed to this much. There are some limitations. More often than not, if you see, most of the algorithm is going to use practically quaternion, which I'll come after this. Now, why it says that? Now, let's say you have a measurement. Let's say two measurements, M and S. What it says that you have 2 measurements. You need to practically get that actually matrix M done. Okay, I define matrix M, measurement U, V, and W. Okay, I have this. And I define what is my U, is a component of M, which is the measurement itself, and V I define as another measurement which is consists of S as well. It's a cross. Then W is basically a cross between U and V. That means there's 2 vectors, so that you will define your fourth or rather third axis. Okay, so when we do this arithmetic, technically speaking, we should be able to define my UVW, which is the measurement, the measurement matrix, so to say. Now, when you want to find the attitude matrix, okay, how to find the attitude matrix between the frame A and B? Again, the same thing. Frame A is local vertical, local horizontal. Frame B is body coordinate. How to do that? When you have already a matrix. When you already have a matrix, how to do that? How to rotate from one frame to another frame? we can simply use the rotation matrix just like in kinematics that we have learned. It's very easy. Okay, so if you want to find their difference, is technically the acute matrix would be basically B, that means a frame B, measurement. You transpose the measurement with respect to the frame A. You transpose that, you do this arithmetic, basically you should be having the actual acute matrix. So it is like this. When you have a measurement, you just have to take this measurement, look at the measurement. You have a X, Y, Z, you have the actual alpha, let's say alpha 1, alpha 2, alpha 3. Take that, rotate that into frame A or B. Now, the exercise that we have done before, all these are given to you, and we just ask you to just rotate from one frame to another frame, vice versa. So this is what is you're actually in the fundamental. This is what exactly is happening, and that is the reason you end up rotating. Okay. Now, go on. This we have also given you quaternions basically. Attitude information, the initial quaternion is given as an attitude input. Then we ask you to, okay, now express this in local vertical, local horizontal, or express this in body coordinate. We have also done that. So the deviation quaternion that always we talk about is actually local vertical, local horizontal, the body coordinate with respect to local vertical, local horizontal. That is the deviation of quaternion that always we've been finding. How this has been actually also done, same method, assume that another two measurements are there. So we have two measurements, as you can see. So each of those measurements, let's say, produces two different coordinate systems. So you have two or three, depending on the two vectors. So let's say I have two vectors. Practically you are forming a coordinate frame A, B, and the reference. What exactly this tells you? You are having a mutual rotations between the two measurements in order for you to find the exact amount of rotated coordinate, so to say, amount of rotated coordinate. So the mutual rotation between the vector pairs determines the unknown rotation around B, which this needs only the S component, which is perpendicular to this. Now, remember how I defined the quaternion. This process is actually is similar to the how we have defined the quaternion. You have a two. In this case, is actually two independent measurement. You start actually rotating it, okay, in the sequence, in order for you to express the difference between them. Okay, that is the fundamental. Now, you don't have to worry much about this because this, it is in a. You need to imagine this. It is very abstract. See how we can apply this. Go on. This is exactly that we have done before. You can imagine this equation. This equation I've given you before. What this says that measurement is given. Now, the slides before this are telling me that means I can, the same procedure that how I have actually defined quaternion, I can apply it in order for me to express what you see here in kinematics form. What I need is, given is basically, measurement is given. What is needed is basically the time evolution of the spacecraft quaternion. That means what? The attitude is what you need. Please refer back to your exact note on kinematics, where I invoke back this. Now, attention need to be given to omega. Please refer back that note. Omega, you'll be very careful of omega. Okay? Now, what exactly this equation helps us to do is this. Initial quaternion, there is a motion, rotational motion in the spacecraft. You update that, you get a new quaternion. And this new quaternion is coming from the actual initial quaternion that we have already defined. Okay? So, every time you are going to the measurement is going to give us this input of omega. Keep on updating this omega. We should be getting a new quaternion, new quaternion, new quaternion, new quaternion. Okay, so accordingly, as you can see, initial, then you have the omega. That means the body, you sense, let's say you have a gyro, you take that input, plug it in here, just like in kinematics, you get a new quaternion. That means that deviation. Okay, then you have a new quaternion, update back. Keep on doing this. This process is going to go on and on and on as long as there is a new omega coming in. That means what? New attitude information coming in. It is going to keep on doing that. Okay. Now, what I can do, same, I rewrite that into a transition matrix definition. This component is practically a transition matrix. Why this is transition matrix? Assume at time 0, this is going to be 1. That means your actual quaternion is equivalent to the initial quaternion. When time 0, when time equals to 1, then time equals to 1, this is going to be 1, and then evolution of the actual attitude is going to happen here. So you keep on updating this, then the value is going to actually change. Okay, then time 2, you will have already, the initial will be at time 1, update this, you get for time 2. Take the time 2 quaternion values, put back here, that is already time 2 value. Now you want to find time 3, look at the measurement again, you will get time 3. It is a very, very simple process and very, very easy with quaternion. We can do this only with quaternion. You want to, well, you can use a DCM, but it's going to become complicated. So if you look at it, it's simple. So what exactly that we do is, rate, let's say rate is coming in, okay? I do integration, 3 by 1 rate. That means what? Roll your pitch. Integration, I get the attitude, right? I get the attitude, that means roll your pitch angle I will get. That's what, this is the exact process is happening here. And this is at time 0. At time 0, that means initial, you should, in a question also we have given you, remember? Initial quaternion is this much. Initial. Done. Repeat this again at time 1. That means the old quaternion will be now the input now. Then you look at the actual new reading, update, new reading, update. So if you ask me how frequent you want to update, that depends on the actual attitude sensor. How fast actually it can give us that actual reading. It can be very fast actually. Yeah. Let's say you want to do it every 1 second. Well, it's fine, no problem. Yeah. Okay, go on. Now, if you look at this alternative to the standard transition matrix routine, I would always advise you to use the transition matrix. That is much easier. Otherwise, you can also do this, but if you look at this, may take you a bit more, well, I would say effort in that sense. So we try not to actually do this. Basically, what I want to explain here, this is one of the alternative. But again, my quaternion propagator is actually defined just like in my previous slide as well. So we keep on updating the actual value omega, yeah, in the propagator. That means this is your transition matrix. We can actually do that. And as you can see, same updates. You start delta t, t1, update this, find the new one, then this goes back here. Okay, update, go back here, read, and then you can get your new one. Okay, so the best is that actually the attitude propagator is easier for you to actually calculate the actual deviation in attitude. Okay, go on. Now, state space, state estimation. State estimation is basically what the fuel measurement is given with respect to the spacecraft attitude. What exactly that you want? You want basically to find the quaternion or the angular rate. This is what it is. This is what it is. So if you use well DCM, then you end up actually finding the angle. If you use a quaternion, you end up finding the Q1, Q2, Q3, Q4. Then practically you can change it to the actual angle. Now, during this estimation process, as I've said, if you want to do estimation, then there is a lot of other models that actually you need to introduce. That means the plant must be there. Then you need to have the disturbance model, and filtering process must be there because there's also noises. That process actually has to come into play in order for you to do the estimation. We won't go into the actual algorithm for this particular subject. I think for master's level we have a course which actually talks about a filtering process, but not actually for degree. Okay, go on. All right. In a nutshell, this is exactly actually what happens. Now, if you have this is on board computer. If you have, okay. Now, if you want to do this, the exact estimation is this one. Now, this model of a spacecraft, dynamics and kinematics. This model is what actually you have calculated. We have derived this model. What model is that? What is your roll dynamics? What is your pitch dynamics? What is your dynamics? So this you have calculated. Then you have a model of attitude sensor. What you are going to use? You are going to use, let's say, a gyro. We can have the plan for this gyro. Okay. Then the correction. That means the measurement. This basically is a correction, optimal correction. What is the correction you need to do? And this can be actually done. This model can keep on actually running on board to do the estimation. Okay. And if you look at it, this is the real dynamics. This is what you calculate. This is exactly when you fly, what happens. This is what it's happening in the real case. This is happening inside your spacecraft. Exactly, you are disturbed. Attitude sensor is actually sensing it, and then your estimation and the actual sensor you can actually compare. So it is like this. Why this is important is because sometimes we have an attitude sensor which is not very good. We don't have a good quality of attitude sensor. For example, let's say we are using a magnetometers to do this attitude control sensing. So then obviously you need a model. Then you look at the actual sensing, and you start actually comparing to get the true best possible attitude. Okay. Now, again back to the kinematic. What exactly that we are doing? We are finding the actual deviation. Okay, deviation, quaternion deviation. Now, reference is given. Reference, let's say the best reference would be, let's give you example 0, 0, 0, 1. That means it is perfect. Quaternion estimate. Quaternion estimate is after you put in the exact disturbance torque, the rigid body is disturbed. So therefore, I should be able to measure my deviation. Remember this deviation. This deviation is measured with respect to the local vertical, local horizontal, with respect to the body with respect to the local vertical, local horizontal. So technically speaking, I should be, remember this formulation, when the angle is very, very small. That means when the Euler angle is very, very small. For a very small angle, this can be used directly, which means that your Q1, okay, this is Q1, Q2, Q3. Your Q1 is exactly what is that? Alpha, yeah, roll over 2. Q2 is pitch over 2, and yaw is over 2 as well. Okay, and fourth axis Q4 is equals to 1, which means that they are almost parallel already. So this is only when is almost 1. If you have a very far, let's say maybe you have a 0.5 or 0.2 Q4, the angle will not be actually very, it will be too big. That means the angle is huge. So for a very small Euler angles, this is actually valid. And I think we have also discussed this before. We will use this, and this can be directly injected into your attitude control loop. Remember that attitude control loop that we have built, reference and measured. So this can be actually injected into the measured. Okay, reference will be always 0. What is the best attitude that you want to get? What is the roll attitude? Roll attitude, I want it to be 0. That means it's perfect. So that will be 0. Then whatever I measure, I have already a control loop. For example, you have done the control loop of reaction wheel. So that will be my reference will be 0. And then whatever I estimate the deviation of matrix, the deviation quaternion, I can actually get all those attitudes. So I can correct them accordingly. Think of that. We will see the last slides. Okay. Again, what I'm doing, this is a deviation or the error, attitude error, and in kinematics we say that how to calculate the deviation. I have a rotation matrix, quaternion rotation matrix. Okay, I have 4 by 4. Then I have the estimate. So practically, what are you doing? That this operation is actually the reference quaternion you minus with the estimate quaternion. So you will get the exact deviation. So we use the same formulation. If you look at the kinematics equation or the kinematics chapter, this is a deviation. Again, it is a rotation. It's a rotation. So 4 by 1, 4 by 4, here 4 by 1, you will actually finally get 4 by 1 matrix. Okay? This is just a control loop. Alright. I think it's just a sort of a small revision how we are going to use those all those operations that we have learned in kinematics to help us to actually estimate the attitudes for spacecraft. Thank you.